Hello again, and from now on it has to be English, I'm afraid. It's a great pleasure and a great honor for me to be here today to meet you all, and I'm very keen that you should know some of the latest developments we have. And some of you will have heard me speak before when I've spoken about the background. So I need to speak again about the background so we all understand this. So if you've heard it before, please go to sleep now, but wake up later. Okay. I want to talk about how we're going to get quality into our metals. And I'm talking about aluminium, steels, ductile ions. The whole range of metals benefits from being poured well. Now, what do I mean, poured well? See, if we can, sorry, let me start again. The central problem is this, that we have our liquid metal here, we have air here, but the boundary is not a liquid. It's usually a solid, a very stable solid. So it's nearly always aluminium oxide. Even with our steels and with copper-based alloys, there's enough aluminium to make this aluminium oxide nearly every time. For some stainless steels, it's chromium oxide. But it is solid. Okay? It's a very thin solid, but there's no problem with it being here while it stays on the top. But it has very special properties. The top is dry in contact with the air, and when you look at it under a microscope, it looks like sandpaper. Okay? But now, underneath, it's in perfect contact with the liquid because it's grown atom by atom from the liquid. So underneath, it's perfectly wetted, the top perfectly dry. Now, this has immensely important implications for our casting. Because now, if I look down into a riser, into a feeder, as the metal's coming up, it comes up in a special way. It comes up by the metal, by the oxide splitting, and you can see this happening. As you watch it, it splits and moves to one side, but immediately reforms and splits and reforms, splits and reforms. And so what you see is that surface oxide becomes the skin of the casting. And it's not inside the casting, it moves to the outside. And we see that on our first slide.
You want to point?
That's the...
Right.
Never mind. Need to go back. Anyway, so we see the metal coming up, it splits and moves to one side, and this gives us a good casting, free from oxides. But we never make castings like that. We pour the metal, and now we pour, and now the surface becomes folded over. Now, this is probably disaster, because now I have a dry side to dry side. There's no bonding between those two. So now I have a crack inside the liquid. And so when we pour turbulently, we are pouring Thank you. We are manufacturing cracks which are tumbling into our liquid and mixing with the liquid. The cracks, once they get inside the metal, there's enough turbulence to do this. And so now we have a very convoluted crack. I usually pass this around, but today I need it today. But you can come and study it afterwards because it's extremely interesting. And you can tell when you move around that it's genuinely a crack. But it's nothing like an engineering crack. It's something very special to castings. This is the kind of thing which you will find in almost every casting you make. But they'll be there in hundreds and thousands. And these things keep the properties down. Now, it gets worse. Because after this is folded in and goes through the running system, along the running system, comes up into the mold, now the mold is quiet. And the metal comes in, and the metal finally stops moving. I have competition. Okay. When the metal finally stops moving, this will now start to open again. And there are all sorts of interesting mechanisms which reopen the crack. And fold by fold, it opens. And each time a little fold opens, and all of these things are opening everywhere, right through the metal. Each time it opens, the properties come down. And then it opens another part, properties down. Opens more, the properties down. And so in our thick sections, we have minimum properties because this has plenty of time to open. In the thin sections, quickly solidifies, it's like that. So our properties are best. They're still not good because these things are always cracks. They always bring the properties down. So this is what I call a bifilm. It's because it's now two films which have come together to make a crack. And interestingly, the outsides are perfectly wetted, remember? And on the outside, we get many different phases will nucleate. So when we're cooling steels from the austenite range, when it changes over to ferrite, the ferrite always nucleates here. So I'm jumping ahead of myself. These bifilms will very often, not always, but often will be sitting at grain boundaries. And that's because a grain will grow and will push. And another grain will grow from this way. And so finally, this becomes the grain boundary. There are still some which are sitting across the grains, but not so many. They're mostly grain boundaries. So whenever I see a precipitate at a grain boundary, I say, it's not sitting on a boundary, it's sitting on a bifilm. And with this sort of knowledge, I've had to completely rethink my metallurgy. In fact, I had to unlearn it and relearn it. But now I feel my metallurgy makes sense for the first time. It's a great relief to think that your metallurgy makes sense. So here we are. You've changed it for me. Oh, thanks. Okay. I need warning of these things. Okay. So the bifilms are clearly very important. Clearly there are cracks, which are major problems. But occasionally, when the surface folds over, it can fold over and take in some air. And this has this special technical name, which I call it an air bubble. Okay? So what it is not is, like in the steels, it's not a reaction between elements like the carbon and the oxygen to give carbon monoxide. It's not necessarily hydrogen. It's just air. And it's a damn nuisance as air. We'll come back to that. So here we are. We're making bifilms by surfaces just impinging or by surfaces folding. And the next slide, we can see something in aluminum, and those pores are air bubbles. Once again, they've been hammered in different directions, and they've got a rigid outer shell, which is the oxide, which means they don't keep the nice spherical format. Here you can see the bifilms because these happen to be very thick. Normally, you can't see them. The oxide is formed so quickly when the metal folds in. It just folds in quickly, and then it's submerged, and it can't oxidize anymore. So there's so little time for the oxide to grow, it only grows a few molecules thick. And so these films are unusual. We have a look at some other films under the microscope. They're only a few atoms thick. Okay. And this is an interesting instance of two small molds in which we took aluminium and we poured it into the two quickly, and then on one of them we put a jar over the top, pumped down the vacuum to about 1/10 of an atmosphere, and what I hoped would happen would be that the small amount of air between the bifilms, because we're at 1/10 of an atmosphere, this would grow by 10 times. And sure enough, on the right you can see that we do have cracks in the liquid that we can see now. But interestingly, look carefully at the left figure. The tiny shadows. Those are the compact bifilms. Okay? Come all the way through the material, you can see them floating about. But as the pressure comes down and the pressure builds up inside here, this inflates it. And so if the pressure comes down because of, say, shrinkage in the casting, then this can open bifilms, and what you can see, this rather funny shape I have, you can see the same funny shapes on the right-hand side. But just look how many cracks we have. It's full of cracks. And that's where our liquid metals now are, and why we're getting poor properties. Not so much poor, maybe, but mediocre. So, move on again. This was just a couple of castings, which we did a 3-point bend. And what you can see, this is a casting with no defects, but this is a casting with huge cracks which have opened up. The important thing to see about these cracks is that they're not along the center of the axis. You would expect with a 3-point bend to have the cracks exactly along the axis of the bend, but they're not there. These cracks are random cracks. They're just occurring anywhere, in all directions. And that tells you that this is not a metallurgical problem. These are cracks which have been introduced into our metal by a random process called turbulence. It's just that we've just folded in and we've messed the liquid about, and we finish with random cracks. Okay. So this is an interesting slide because I just throw it up because when we come to think about the properties of our metals, and particularly cleanness of steels and our steel castings, we're all of us trying to get rid of inclusions because we say the inclusions are strong and brittle and they form cracks. And so the normal thinking of interpreting this view that we would see under the microscope would be that the inclusion is there first, we put on a stress, the inclusion cracks, and the crack can go into the matrix. Now, unfortunately, that's completely wrong. Okay? The reality is that the crack is there first, and the inclusion nucleates on the crack, and there's no stress involved at all. Now, that takes some believing, but when you follow it through, the logic is perfect. So we have to rethink what we're doing with getting clean steels. The real thing is not to introduce cracks into our steels. That's the first thing that arrives here. The crack is there first, you remember? And then all the other phases, generally speaking, nucleate on the cracks themselves. They're not kind of normal cracks. These are what I call oxide cracks or bifilms. But you can see how dangerous they are because now we've got other phases on which now appear to be brittle. As a matter of fact, nearly all these phases, like carbides in steels, they're all beautifully ductile. And they're extremely crack resistant. It's just that they are full of cracks because they've nucleated on cracks. So you can see the kind of rethinking we're going to have to do to understand our metallurgy. Okay. So let's move on from liquid metals and metallurgy for a moment and talk about some technology. So here we are as steel people, and here we're absolutely wrecking the quality of our liquid steel. You see, in the furnace, it would have been in the furnace perhaps an hour. So in all that time, and it's not deep, it's only half a meter deep or so in the bath of steel. There's plenty of time for all the damage that's in there to float out. Plenty of time. But then we go and tip the furnace up and tip the metal out, and it falls through a height of, say, 3 meters, and now smashes up and makes the melt full of defects. Now, fortunately, we spend time then taking the ladle out of the pit, carrying it over to where the casting is going to happen, lowering it down, getting it into position, and finally opening the nozzle, pouring our steel. So by that time, lots of that damage has floated out and become a slag layer on top of the steel. So the steel is now good again. But now we go and make it bad once again by pouring it down a terrible running system. So folding in more defects for a second time. Now, it's not necessary to do this. And in a moment, we'll come on to that. But let's have a look at what happens in the aluminium industry. And it's not this man's fault that the steel is being ruined. Aluminium being ruined here. And all our foundries, I'm sorry to say, our foundries are totally badly designed. There's no choice but to ruin the quality of the metal here at this point in the process. You have to do it. And this need not happen. The furnace need not have been built this way. And that makes me furious. And all the foundries I deal with today, I never allow pouring anywhere in the foundry. Not at any single point is the metal poured. And then you win. Then you get really good castings. Okay. Anyway, let's move on. So one of the big ways to get this nice filling method whereby the metal is coming up and moving to one side, so we never get the surface oxide into the metal. It always becomes the skin of the casting. That is counter-gravity casting. And it really does make good products if it's done correctly. And there are plenty of ways of doing it badly. Okay, so this looks like a good idea. So you'll all know about low pressure die casting. Most of our wheels are made this way. And we put a pressure into the pressurized furnace. The metal lifts up the spout. It goes up the spout in the correct way, into the mold in the correct way. But the product is awful. And all of our wheel makers struggle with the quality of the product because of the prevalence of bifilms. The metal is just full of bifilms. And the next slide shows where they come from. You see, the forklift truck arrives here, tips into the basin here with horrible turbulence. And then it falls again, a more horrible turbulence. And all that bad metal is then goes into the casting to make the casting. And then the gas pressure is switched off when the casting is solid. And the metal falls down here, so it goes whoosh, to stir up the metal again to guarantee that the metal is as bad as possible for the next casting. Okay? So this is not my favorite process. I think this process is not workable, actually. Now, there are some better forms, and you all know that you can swap the furnace around. And so, but that the whole business of casting into a die and having to wait while your metal goes solid so that with a wheel, if you're lucky, you can make a wheel every 3 minutes, or if you water cool your die, which is, I hate water cooled dies, but you can get down to 2.5 minutes. But with sand, if this was sand casting, we could make a casting every 45 seconds. I mean, sand casting is a powerful, rapid production process, which if you can fill it by counter-gravity, is amazingly powerful. We should all be thinking about it. Okay. So, years ago, this was my first effort at, it's so long ago, I've forgotten when it was. It's about 1980, I think. I'm giving my age away. But this process was fairly successful. In fact, Cosworth had engines which every year were being increased in power. And finally, the engines were blowing themselves apart. And of the castings they used to have, 50% of engines failed on the test bed from fatigue. They never got out onto a racing car. And so I was invited to think about a new foundry for them. And I said, this is what we're going to do. And we did it and made our first castings after it took us 13 months. But anyway, when the first castings arrived, no engine ever failed again by fatigue. So it went from 50% failures to 0 failures overnight. So we knew we were doing something right. Frankly, there's all sorts of things wrong with the process, which I look back at now. But frankly, it is used around the world, and people are reasonably happy with it. And but Ford and GM in North America both use this process. Okay. So what if we were to use gravity and to pour by gravity? The real problem is the cone. that leads into the running system. And we all pour down a cone. Everybody in the world uses this. But if I draw a cone to my chemical engineering friends, and I say, what have I drawn? Now I'm putting a fluid down the middle and I've got a cone. Oh, they say, it's obvious. It's a pump. And it's a pump for pumping air. Okay? So the cone takes in huge quantities of air. And I'd like to show you. Let's move on and to the next slide. And yes, here we are. These are the ways one could make a simple casting like an ingot. You could top pour, which is very bad. You could bottom gate, which happens to be very bad because we're taking air at the conical, the cone there. And the next slide, here we are. If you do a contact pour, suddenly it transforms the casting process. Now, I've just got 2 minutes of my time to make a simulated contact pour, and now I'm going to do a contact pour of one simulated lungful of liquid steel. Find out what the volume is. It's a little deaf of me. And then I always feel ashamed of this. You'd think I could do better than that. Anyway, that's it. That's the contact pour. Now, I'm now going to do a pour into a conical basin. I can form a conical basin. Okay. You can see why your castings are no good. They are full of air and oxides and bifilms, and you never ever make a good casting pouring down conical basins by gravity. It's not possible. Tomorrow I have a chance to talk for 20 minutes to you, to talk about the solutions to this problem. And the solutions are in my new little book. It is only a few weeks old now. I think it's just about a month old. It's the latest edition. But, in here are these new gravity pouring systems, which I can't tell you how delighted I am to finally get them. Oh, beg everyone's pardon. I'm so delighted that I'm able finally to present to the world solutions to this problem, because frankly it's a massive problem. We really need to do something about it, and unless we get the running systems right, we shall never achieve it. Preferably we'll do all our castings by counter-gravity, but until then we have to earn an honest crust, and when we've earned enough money, then we can launch into our counter-gravity. Mr. President, I'm overrunning my time. Thank you.